Hey y'all, we are Memphis Communiversity and we're back for another Calculus Done Wrong lesson where we wrong calculus before calculus wrongs us. And today we are going to be continuing our shape of curves unit and we are going to be finding absolute max and absolute min of functions. So instead of finding the relative maximum or the relative minimum, that's the previous video that we did where we were trying to find every single hill and mountain and every single valley. In this case, what we're trying to do is we're trying to find the highest mountain and the lowest valley. So we're trying to find the absolute max of a function over a closed interval or the absolute minimum of a function over a closed interval. So what we're going to talk about today is we're going to talk about two ways to find absolute max or min. And basically it's whether you're finding the absolute max over an interval or are you finding the absolute max over the entire number line. So for the first way, when we have a closed interval, we're going to be using what is called the closed interval method. And you might imagine why. It's aptly named. So it's going to be a three-step process where we're going to employ the same three steps over and over and over again. For the question where we want to find the absolute max over the entire number line, that's going to be really similar to our rel max video, where what we're going to do is we're going to draw a sign chart and we're going to write a sentence, which is going to be the first derivative test for absolute extrema. So let's get started. We do have a lot to do today. So again, what we're doing today is absolute max, absolute min. So I'm going to abbreviate that abs max, abs min over a function, so of f. So the first way, let's try to write this a little bit better. So abs max min of a function f. So again, for this first half of the video, what we're going to talk about is the closed interval method. And the closed interval method is far more important and you'll use it far more often than the second half of the video, the first derivative test for absolute extrema. So for the closed interval method, again, part of the givens are going to be some sort of closed interval. So you're not finding the absolute max or min of the function over every single number. You're only finding the absolute max or min over the numbers, for example, -1 to 3. So it's a three-step process. So the first step is the easiest step. It's locate the function. So basically, there might be multiple functions in the question. This step might be the given function, but always we're going to locate the function. What do you want to find the max or min of? And we're just going to write it nicely. Even if it is the given, we're still going to write it because it's easier to plug in numbers eventually in step 3 if we just have the locate function in our own handwriting. So I like to write the locate step even if it's sort of trivial, and in some cases it's not trivial and I'll miss the question less if I write it. So the second step is critical points. So critical points. And critical points are where the derivative equals 0 or potentially non-existent. In most cases, it's where the derivative equals 0. So what we're going to do is we're going to take the derivative of step 1 and set it equal to 0. The third step, which is the most fun step or the least fun step, is just drawing a table. So what you're going to do is you're going to have a two-column table where on the left side you're going to have your x's, so your potential candidates for max or min. What goes in that left column will be the closed interval. So A and B will definitely be in the interval. And then also what will go in this interval are the critical points from step 2. So critical points from step 2. Keeping in mind that you only care about the closed interval. So for example, if your closed interval is something like 0 to 6, and your critical points are 2 and 7, you wouldn't include 7 in this table because you only care about the world from 0 to 6. So you'd only include 2. So again, for this table, you always include at least 2 points. Those are your endpoints that are given. And finally, you include any critical point from step 2 that fit within that interval. Finally, you need to find the right column, but to find the right column, what you do is you plug in these numbers. So you could have 2 numbers, you could have 4 numbers, whatever. You have at least 2 because you have at least 2 endpoints. And you're going to plug these numbers into the locate step. So that's why we like to write the locate function, because eventually the locate function might get pretty complicated. But again, it's easier to plug in a function if you can just visibly see it on your page. Finally, the maximum will be the biggest number and the minimum will be the smallest number. So the max will just be the biggest number and the minimum will be the smallest number. And we didn't prove why this sort of process works, but the process works because, again, relative max occurs at critical points and relative min occurs at critical points. But if you're cutting off the function, the maximum might occur on the endpoints, so that's why we do this sort of process. But again, it's a process that you'll come to love because on, for example, the free response question on the AP exam, a lot of free response questions, particle motion, accumulation free response questions like rate in, rate out, they all have this absolute max or min question. So let's practice this. We might as well get started. But again, it's a 3-step process. Locate the function you're taking the max or min of. Second step is take the derivative, set it equal to 0. Third step is plug in the endpoints and any critical points that fit within that interval into your function and just compare biggest and smallest. So let's do the first one. So I'm gonna erase this. I'm gonna erase this nicely. So let's say we're finding the absolute max or min. So finding the abs max and the ab min. Sometimes they only ask one, of course, but in this case, we're just gonna do both. So the abs max and the abs min of f of x. And we're gonna have an interval. Our interval is going to be, let's say, 0 to 3. And then finally, we're gonna have a function. Our first function is gonna be f of x. It's going to be, let's say, x cubed plus 6x squared minus 15x plus 1. So this is gonna be my function here. And then we're gonna start the question. So again, when you see the words absolute max or min and you have a closed interval, what you want to think about is the closed interval method. So it's always 3 steps. So we're just going to proceed with those 3 steps. The first case, which in this case is trivial because the locate is the given, I still like to write it down. So I'm going to write locate. We're trying to take the max or min of f of x right here. So I'm going to write f of x. So it's going to be f of x equals x cubed plus 6x squared minus 15x plus 1. Again, sometimes it does match the given, but I still like to write it every single time, just so that when I plug in numbers, I can maybe plug in numbers more easily. Step 2 is take the derivative. This is the key step. It's really take the derivative and set it equal to 0. So these are our critical points. Let's take the derivative. Here we're using the power rule, of course, no product rule, where you just take the power, drop it to the front, subtract 1 from the old exponent. So it's going to be 3x squared plus 12x minus 15. Keeping in mind that this is a little bit different than, of course, our relative max questions, our concavity questions, our increasing, decreasing questions from the previous videos, because in these questions, you don't draw a sign chart, you draw a table instead. So the closed interval method is sort of the odd stepbrother of these sort of questions, but it's still a very important question because it appears very often, and sometimes you want to find the max or the min of something. So at this step, we do need to set this to be equal to 0, but I'm going to factor it a little bit. Looks like I'm going to take out a 3, so it's going to be 3x squared plus 4x minus 5. Then I'm going to factor this. It's going to be 3 times x minus 1, I believe, plus 5. And again, you're not just taking the derivative, you're setting this to equal to 0. So let's see if we can squeeze in a 0 equals here. So it looks like my x's are going to be 1 and negative 5. So that's that. So now I'm ready to draw the table. You don't have to label it as a table. I think it's pretty obvious that it's a table. So again, I always do my left column first because I like to see what numbers I'm going to plug into my function. You always plug in these numbers, the given closed interval. You don't get to choose these numbers. These numbers come with a question. So we're going to include 0 and 3. Then you look at your previous step and you include critical numbers that fit within that interval. Keeping in mind in this case that, for example, negative 5 does not fit within 0 and 3, so we don't even consider it as a potential absolute min because it's not in the interval that we care about. So in this case, all we're going to do is plug in 1. So these are 3 numbers. Again, it's the endpoints and the critical point. Finally, you're going to plug in these numbers into the locate step. Sometimes, again, the locate step won't match the given function. We'll see an example of that, I think, in example 3. But in this case, it does match the given. But no matter what, I just plug it into the locate. So it looks like when you plug it into the locate, it does involve some math, of course. Looks like we'll get 1 when we plug it into 0. If we plug in 1, 1 plus 6 plus another 1, that's 8 minus 15. That's negative 7, I believe. And then finally, when you plug in 3, maybe we can do some work on the side and then erase it. 3 cubed plus 6 times 3 squared minus 15 times 3 plus 1. Well, it looks like this has a bunch of 3's in it. So if I take out a 9, it should be 3 plus 6 minus 5, I believe, plus 1. This doesn't look too bad. It's going to be 6 minus 5 is 1, 1 plus 3 is 4. So I'm just doing math. Perhaps you have a calculator so that you can do this in a calculator. But 6 minus 5 is 1, 1 plus 3 is 4. 4 times 9 is 36. So it looks like we're going to have 37 here in the end. So 37. And then finally, you don't even need to memorize the sentence because it's just the biggest y value goes with the max, the smallest y value goes with the min. So I like to write it in terms of a quick little recap. So keep in mind that sometimes they ask where the absolute min occurs, which would be, for example, at x equals 1, and sometimes they ask what the absolute minimum value is, which in this case is -7. But I like to write both things. So the abs min value is -7 at x is equal to 1. Basically, I like to include the x coordinate and the y coordinate. And the abs max value is 37 at x is equal to 3. So again, this is the absolute maximum random process, and you're going to do this quite often. So again, to find the absolute maximum min, you first locate the function, which might match the given, might not. Then you take the derivative, set it equal to 0, start trying to simplify as much as possible, factor it. And once we get the factor, now you're ready to form the table, the most exciting step, of course. So you always include the endpoints, and you might include critical points depending on if they're in the interval. So we did include 1 because 1 is in between 0 and 3. We did not include -5 because -5 is not in between 0 and 3. Finally, you take your numbers, and the most important thing is that you plug it into the correct function. Sometimes there's going to be like 4 or 5 different functions, and you want to plug it into the correct function because it's the very last step, and you don't want to miss the last step. So in this case, you always plug it into the locate, the thing you're trying to find the absolute max or min of. So we plugged in 0, 1, 3 into this locate, and we just got values. This was the minimum, this was the minimum, this was the maximum, and that's how it works. So let's do another question that's pretty similar, and let's just do a few more, and then we'll talk about the alternative way to do absolute max or min. So it's again the same 3 steps. Just locate the function, take the derivative, set it equal to 0, start forming that table. So in this case, what we're going to do is we're going to do a new function. It's going to be the square root of 4 minus x squared. And finally, we're going to do the interval -1 and 2. So this is my next question. So again, let's first just start going through the process. First step is locate the function. In this case, just like the previous example, the locate is the given, but keep in mind that sometimes this will not be the case. So in this case, the locate is the given. I'm going to still write it because I like to rewrite it because I like to do the same thing every single time. Locate the function I'm taking the absolute maximum min of. The second step is take the derivative. So perhaps we should write this as 4 minus x squared to the -1 to the 1/2, so that we're about to use the power rule. I do this anytime I'm taking derivatives, of course. Remember that this is the power rule, so we're going to take the 1/2, bring it to the front, subtract 1 from the exponent. So it's going to be the critical point step is going to be f prime of x is equal to 4 minus x squared. We're going to bring the 1/2 to the front. We're going to subtract 1 from the old exponent. 1/2 minus 1 is 1/2 minus 2/2. That's -1/2. Keep in mind though that when we're taking derivatives, we still of course have to take derivatives correctly. We have to remember the most important thing when you're taking derivatives, and that of course is the chain rule. So we do need to remember the chain rule in this case. There is an inside function, so it's not just this derivative. We do have to multiply by the derivative of the inside function. The inside function being 4 minus x squared, so its derivative is -2x. So we're going to multiply by -2x, and this is the derivative. What we need to do is we need to set this derivative to be equal to 0, and also to see where the derivative doesn't exist, keeping in mind that critical points often is when the derivative equals 0, but potentially you might have the derivative not exist, for example in this case. So what we're going to do is we are going to write equals 1/2. We're going to change this back into a square root because it'll be easier to deal with. 4 minus x squared, root that, so we can erase these parentheses and just write a root. 4 minus x squared, and then on the top here, it looks like we have -2x. The 2's cancel, so I'm just going to simplify this to be -x over the square root of 4 minus x squared. Keeping in mind that again, what we're doing is we're setting the derivative to be equal to 0, or we're seeing where this doesn't exist. This thing right here equals 0 when the top is equal to 0, so it looks like we have one critical point at least, x is equal to 0. Finally, it doesn't exist when the denominator equals 0. Well, when this fraction, this denominator equals 0, looks like we're going to have 4 minus x squared equals 0. So that means x is equal to 2 or -2. So x is equal to plus or minus 2. So it looks like these are 3 critical numbers. Again, remember that critical points aren't just where the derivative equals 0. That does work for a lot of the questions. But if you have these nice, tricky questions, you might have more zeros. But it's not any more difficult. You just include the zeros of both the numerator and the denominator. in this case 0, and plus and minus 1, 2. So now it's the fun step, now it's the table time. So we're going to draw a nice little table. Again, the first zeros that I always consider in the table are just going to be -1 and 2. So we're going to put -1 here, we're going to put 2. Then we're going to look at all of our critical numbers. Looks like we have 0, 2, and -2. 2 is already in the table, so we don't need to add it twice, because then you would just be finding the value twice. 0 is certainly within this table, but keeping in mind that -2 is not within this table, so that's why we're not going to include it. Finally, once you have the numbers that are ready for your right column, meaning the endpoints and the critical points that fit within that interval, now what you do is you plug into the function, and then we should be able to solve. So in this case, when you plug in 0, you're going to get square root of 4, that's 2. I don't know why I'm doing them out of order, but whatever. When you plug in 2, you get 4 minus 4, that's 0. Again, you're always plugging it into this locate function, which might not match the given. That's going to occur in the next question. Finally, when you plug in -1, it looks like you get square root of 3. If you don't know, 2 is bigger than the square root of 3, because 2 is equal to the square root of 4, and the square root of 4 is bigger than the square root of 3. So it looks like this will be the max, and this will be the min. So let's write that down. So the abs max is the number 2, because that's the highest y value, and it occurs at x equals 0. Finally, the abs min is 0 at x is equal to 2, because that's the smallest minimum value. So again, just the same 3 steps. Locate the function you're taking the max or min of. In these first 3 questions, it was trivial because it matched the given, but sometimes it won't. Second step is take the derivative, set it equal to 0, it does not exist. Take the derivative carefully, of course. If you need to multiply by the chain rule, you need to multiply by the chain rule. Finally, when you're doing your table, critical points, also the endpoints as well, plug it into your locate. Compare which one has the biggest and the smallest value. So it is quite a bit of a process, but it's the same process every single time, so we're not going to mind. So let's do another question. Let's do a final particle motion question where finally the locate is not trivial. So in this case, what we're going to do is we're going to find the absolute max or min of acceleration. So we can write words out. Of some sort of particle. Remembering that in particle motion, it goes position, velocity, and then acceleration. So we're finding the absolute max or min of acceleration of a particle whose velocity is v of t equals t cubed minus 3t squared plus 6t minus 1. And what we're going to do is we're going to find this over the first 3 seconds. So hopefully you can read this. Again, it's an absolute max or min question. Find the absolute max or min of an acceleration of some particle whose velocity is given, and we want to find it over the first 4 seconds. Keeping in mind that the first 4 seconds means the time interval from 0 to 3. So first 4 seconds is that closed interval that's always given. In this case, so it's 0 to 3. So what we're going to do is we're going to start the process just like normal. If I don't work out the function. So locate. So here again is the first time where the locate function is actually not a trivial step. So notice that in this question, we're finding the absolute max or min of acceleration, but we're given the velocity. And of course, velocity does not match acceleration. So what I don't want to do is I don't want to find the maximum or the minimum of the function given, because that would be doing my own question, which is great, but sometimes it's good to answer the questions on assessments. So I don't want to find the absolute max or min of velocity, so I'm not going to put velocity in the locate. What I'm going to first do is I'm going to take the derivative, because that's how you find the acceleration from velocity, and I'm going to work with that as the locate. So in this case, I need to take a derivative just to get to the locate step. Whatever you need to do, if you need to run around the world just to get to this locate step, you have to do it. So in this case, to get to the locate step, I do have to take the derivative, of course, with the power rule. So it looks like the derivative of t cubed is 3t squared, of course. The derivative of minus 3t squared, you take the 2, drop it to the front, let them mingle a little bit. That's going to be a 6. Subtract 1 from the exponent. And finally, the derivative of 6t is just 6, of course, because the derivative of any constant times t is that constant. So it's going to be plus 6. Once I write this question right here, I'm no longer looking at velocity at all for the rest of the question, because again, the thing I care about the most is the locate step, the acceleration itself. So the next step is take the derivative, critical points. And again, you're taking the derivative of the locate step. You don't care about the velocity anymore. I won't look at the velocity at all. So what's the derivative here? Doesn't look too bad. Again, it's the power rule, so it's going to be 6t minus 6. Taking the 2, bring it to the front, subtract 1, blah, 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 blah. You set this to be 0. This one doesn't look too bad. It's going to be t is equal to 1 is my critical point. Finally, I'm ready for the table. So we have t's, and we have a of t. So again, first 3 seconds implies that our interval that we're dealing with is from 0 to 3, because you're starting off at t equals 0, going to 3. That's what the first 3 seconds means. So it's 0 to 3. We are going to include this critical point of 1 because it fits within the interval. So that's a nice little 1 there. And the key though, the thing that students mess up all the time is that they'll plug in 0, 1, and 3 into the wrong function. Here we have v of t, here we have a of t, here we have a prime of t. But if you do this question and this sort of method very precisely, locate critical points table, you're not going to miss it because you always plug it into the thing you're taking the max or min of, and that's the locate step. So again, when I take this 0, 1, and 3, I'm certainly not going to plug it into this function right here. I'm going to plug it into the locate thing, the thing I'm trying to find the max or min of. So let's do that. So when you plug in 0, it looks like you're just going to get 6. When you plug in 1, it's going to be 3 minus 6 plus 6, so it's just going to be 3. And then finally, when you plug in 3, let's see if we can do some math. 3 times 3 times 3 minus 6 times 3 plus 6. Looks like everything can be divided by at least, we can just find this out, 27. We don't have to be tricky with our math. Let's just find this. So this can be 27 minus 12, so I believe it's 15. Is that right? 27 minus 8? Yes. So we're going to have 15 here. Then we can erase our sort of math shame that we couldn't do in our head. But here we go. Again, we're ready for the answer. So the maximum acceleration looks like it's 15. Is 15 at t is equal to 3. And the minimum acceleration is 3 at t equals 1. So again, nothing new from the previous questions. It's still locate critical points table, except that the locate was not the given itself. So we had to find the locate first by taking a derivative, and then when we drew the table, we did not plug in any values into the given, because the given we don't care about anymore. We only care about the thing we're taking the absolute max or min of, and in this case, it was acceleration. So that's the closed interval method. Again, you're going to get very accustomed to it because you're going to do it quite often. It appears on every single AP exam and probably every single college calculus exam. Locate the function, take the derivative, set it equal to 0. There's the critical points. Finally, table. But for now, what I'm going to do is I'm going to talk about the alternative way to do absolute max or min. So basically, you do this method when you can't draw a table. And a big reason why is because there's no endpoints. And if there's no endpoint, you can't draw the table because always the endpoints go in the table. So let's talk about the alternative way to do absolute max or min. So the alternative way to do absolute max or min is sometimes called the first derivative test for absolute extrema, but I like to call it the alternative way. We can talk what books call it, I guess. So we're doing the first derivative test for extrema, for abs extrema. Again, you do this method when you do not have a closed interval. And you only can do this method for very precise things. So you can only do this method when f prime of x has a very simple sign chart. So the sign chart of it is either going to be this, either a line going from negative to positive, or the sign chart is going to be just the opposite. 2 intervals where it goes positive and then negative. So hopefully from our rules about derivatives, you know that this has to be an absolute min, for example. And why is that the case? Well, if your derivative is negative, that means you have negative slope. And then if your derivative is positive, that means you're going to have positive slope. So at this point, you go from negative to positive. So that has to be the absolute min. And notice that the sign chart doesn't change at all anymore. So that thing has to be the absolute min. So what we're going to do is we're going to write a sentence that's not exactly the relative min sentence or the relative max sentence, but it's really similar. Basically, we're just trying to describe the sign chart as best as possible. It's negative for x smaller than a, and it's bigger for x bigger than a. So that's what the sentence is. F has an abs min at x is equal to a because f prime is negative. So I'm just describing the sign chart again. It's negative for x smaller than a, and it's positive for x bigger than a. Keep in mind that this is different than the relative min statement or the local min statement. The local min sentence says that it goes from negative to positive, but just because I know it goes from negative to positive doesn't imply that it's an absolute min, because I don't know what happens anywhere in the interval. But this sentence is more specific. This sentence says it's only negative for x smaller than the number. It's only positive for x bigger than the number. F prime doesn't do anything else, so this has to be an absolute extrema. So again, for this method, it's only for these small little cases, and these small little cases sort of have these arguments with easy sign charts. The absolute max sentence will be very similar. Keeping in mind that you cannot do absolute max with this one, you only can do absolute min for this one. So usually these questions sort of magically occur that you'll have the right answer. So in this case, it will be F has an abs max. Again, all I'm doing is describing the sign chart. Some of my students like to memorize these sentences, but I don't have to memorize them because I'm just looking at the sign chart and coming up with a sentence. All I'm going to write is that F prime is positive for x smaller than a, and F prime is negative for x bigger than a. That's all it does. It goes from positive to negative and doesn't do anything else. So F prime goes from positive to negative, and that's all it does. So absolute min is negative to positive, absolute max is positive to negative, but again, you don't want to write that perfect relative max or relative min sentence. You want to write this sentence because this describes the sign chart as well as possible, as precisely as possible. So let's do maybe 2 examples of this and let's call it a day. So let me erase this. So let's erase this. So what we're going to do is we're going to find the absolute minimum, the absolute minimum of the function x squared plus 8x minus 2. So again, if I were given a closed interval, then I would immediately employ the closed interval method, look at the function, take the derivative, draw a table, plug in those numbers into the table, into your locate step. But in this case, because we don't have an interval, we have to do the alternative way. So again, what the alternative way says is you start off with basically the same way. You take the derivative, you get 2x plus 8, in this case because of the power rule. Then you draw the sign chart of this derivative, keeping in mind that this sign chart looks like it goes through, I believe, -4, because you can solve this, bring the 8 over, -8, divide by 2, so you're at -4. And then there's only 2 kinds of lines in the world, so this is a pretty simple sign chart. Because this is a positive slope line, keeping in mind that I don't base it based off the x-intercept, I base it off the slope, mx plus b, looks like it's m is 2, so we have a 2 here. So it's 2 to 4. And then finally, we have to justify because on the AP exam, unfortunately, and potentially college calculus exams, sign charts give you no points. You have to justify that it's a min. So let's justify that this x coordinate is a min, and that's going to be the sentence that we wrote earlier. Again, all we're doing is we're describing the sign chart. I don't know why I wrote 2 and 4 here. I meant negative and positive. That was a weird brain fart. So again, F has an abs min. At this number, x is equal to -4, and it's because it goes from negative to positive, and that's all it does. So F prime is negative for x smaller than the number. F prime is negative, we can write because. F prime is negative for x smaller than -4, and then F prime is bigger, it's positive, for x bigger than -4. So that's going to be the absolute min. Keep in mind that in this case, we only found the x coordinate, so x is equal to -4. Potentially, if you need to, you can find the y coordinate. So if you plug in the y coordinate here, looks like it's going to be -4 squared plus 8 times -4, and then we're going to subtract off of -2. So write -2 here. So it's going to be 16 minus 32, -16 plus -2 again. So it looks like our y value, if that's the number that they want you to find, is -18. But again, this is the main sort of canonical example of trying to find absolute max or min when you don't have an interval, because you can't do the closed interval method. You're going to be doing the closed interval method a lot more than this, but it's still nice to know. All you do is you take a derivative. You hope that the sign chart is this easy. It goes from negative to positive or positive to negative. You write this lovely little sentence right here to justify that we do have an absolute min here because the derivative only is negative for x smaller than -4. The derivative is positive for x bigger than -4. And then finally, if you need to actually find the y-coordinate, you plug it in. So let's do one more example of this, a slightly harder example, and then we should call it a day. And I think we should be at least, if not experts of absolute maximum, certainly better than what we started off with. So let me erase this. So what we're going to do is we're going to find the absolute min. So find the abs min again of this function right here. I think this is what I want. Hopefully this is what I want. Where x is greater than 0. So find the absolute min where x is greater than 0. So this is what we're going to go for. So again, because we don't have an interval, all we're going to do is we're going to start taking the derivative. Because I want to use the power rule as much as possible, I'm going to write this as x plus 4 times x to the -1. Just a nice normal rule. If you have fractions like this, it's so much easier not to do the quotient rule and just change it to a negative exponent so that you can do the power rule instead. So let's do that. F prime of x seems to be 1 minus 4x to the -2 in this case. Because we take the -1, drop it to the front, so the plus becomes minus. -1 minus 1 is -2. Of course, it's easier to maneuver fractions when you have fractions, so I change things to negative exponents when I want to take integrals or when I take derivatives, sort of like with square roots as well. But if I need to work with them any further, I change it back to a fraction. So in this case, it's going to be 1 minus 4 over x squared. I do need to draw a sign chart of this. And if you watched our sign chart videos, you know that in order to draw a sign chart of something, you need to simplify it and factor it as much as possible. In this case, we have two different fractions. So what I need to do is I need to take these two fractions and combine them together so that'll be easier to find the sign chart. So in this case, I'm going to use a common denominator. Looks like my common denominator is just going to be x squared. So I'm going to get x squared minus 4 over x squared. So it looks like we're just going to simplify this. Again, we're just going to factor as much as possible, x minus 2, x plus 2, and then x squared. Keeping in mind that you don't need to be scared of sign charts of fractions. Remember, it's the same thing as sign charts of regular functions because we're drawing sign charts and not graphs. So let's get started with this sign chart. So because we're dealing with f prime, remember you want to count your zeros. You're doing the squiggly line test, if whatever you want to call it. But you count your zeros, so this is 1, 0, 2, 0. But because this is x squared, it contributes 2 more zeros. So we have 4 zeros in total. So there's going to be 4 zeros. That means that it's an even function, so it looks something like a parabola at the end. Then because this is a positive thing, we factored as much as possible. Looks like we have a positive even function. Keeping in mind that positive even functions look like parabolas, so they start at the top and end at the top. So positive even. Don't be intimidated by fractions. Even if you have all these zeros, you just plot all the zeros that you see. So it looks like we have -2, 0, and 2. -2, 0, and 2. And then again, we're starting at the top, ending at the top. And finally, for zero behavior, what you do is you look at the factor that corresponds to each zero. If its power is odd, it goes through. If the power is even, like squared, for example, it will bounce it, meaning f prime. So again, watch our sign chart video if you need more practice with this. But because this is a 1, this is a 1, and this is a 2, it'll go through at these two, and then it'll bounce at this one. So it's going to go through, bounce, and then go through. So this is my sign chart, plus, minus, minus, plus. But you might be wondering at this moment, well, you just said earlier that the sign chart has to be so easy. It has to either go from negative to positive or positive to negative, and it can't do anything else. And in this case, it looks like it's doing a bunch of little things. It's positive, negative, negative, and then positive. That's why we have this little fact at the beginning of our question. What we can do is we can ignore this half of the sign chart. We don't want to ignore it until we have the full sign chart so we have an accurate picture. But because we're dealing with x greater than 0, notice that if we ignore this sign of the sign chart because we don't care about any of the values over there, looks like we have something that we want. Something that goes only negative and then positive. So now all we have to do is justify, and then we can plug in 2, and we can be good to go. So in this case, again, the justification is a nice little sentence describing this sign chart. F has an abs min. Abs min, hopefully my marker doesn't die. x equals 2, and again, you're just describing the sign chart because f prime is negative for x smaller than 2. F prime is negative for this half of the sign chart, and then f prime is positive for x bigger than 2. I used A because that's the general sentence, but it's 2. So then what's the absolute max? Where does it occur? Or the absolute min, sorry. The absolute min occurs at x is equal to 2. And if you want to find the value, well, you're just going to plug in 2 into the function. So the minimum value doesn't look too bad. It's going to be 2 plus 4 over 2. So that's going to be 4 itself. So the x coordinate is 2 and the y coordinate is 4. So that's how you do absolute max or min. So again, what you really want to know is not this latter half of the video. It was really the former half of the video, the closed interval method. Locate the function, take the derivative, draw a sign table, plug in the critical points, which is where the derivative equals 0, into your table. Make sure you have the right function, the locate function. If you want more practice with the closed interval method, what I would highly suggest you do is watch our Girls Teach Calculus video, where one of my former students practices several of these examples, where she goes over very standard questions, but also tricky questions like the given doesn't match the one you want to find the max of, sort of like in those particle motion questions. So be on the lookout for that. I'll link that in the description below. We also have this thing called the alternative way to do absolute max or min, where we go, when we don't have an interval, where we have to justify everything with a sign chart and a sentence. Keep in mind that, again, that's not as important, but if you want more practice with that, this method is used in a video called optimization, because optimization often justifies their absolute max or min using this process. So go check out that video. Hopefully this video was useful for you. You know how to take absolute max or min either through the closed interval method, locate, function, critical points, derivative. Sorry, I don't even know what I'm saying anymore. Locate function, critical points, which is the derivative equals 0, table into the locate, and also the alternative way to do max or min. You take the derivative, draw a sign chart, and you write a sentence. Negative for x smaller than the number, positive for x bigger than the number. For absolute min, it's the reverse for absolute max. But again, this has been quite a long video, but again, hopefully it was useful for you. Thanks again for watching just like normal, and I hope to see you next time.